talking. So RF cavities are probably one of the chief devices people use for accelerators for RF. And it's pretty much easy to make anything resonate. As looking at these cams here, you can almost make anything resonate. It's a question of whether or not you can make it resonate well enough to accelerate a particle. So we'll kind of talk about that today. We'll talk about basically, we'll talk about modes. Everybody talks about modes in the cavities. We'll talk about using a simple model to discuss things, and this model makes it easier than you don't have to go to Maxwell's equations all the time. We'll talk about how to get energy into the cavity. We'll talk about how well you can store energy in a cavity. We'll talk about how you actually do some measurements. We'll talk a little bit, if we have time, we'll see if we have time to talk about power amplifiers. And I don't think I have anything on beam loading that I'm going to talk about today, so maybe we'll get into here, but mostly we'll spend all the time doing this. Okay, so for circular accelerators, you can prove to yourself that only a time-varying electromagnetic field can be used to accelerate the beam. And you can be very fancy about this. You take a look at Faraday's law. E dot dl is equal to the integral of B dot ds, the time derivative of that. So you see this integral E dot dl, that's the energy of a particle gained going around a circle. All right? So you can see if you don't have any dB dt, you have no d, you can't have any E dot dl. So you can never make a DC accelerator with a circular accelerator, and that's kind of a no-brainer because basically it's a short circuit. So you didn't need to have Maxwell's laws to tell you that, but basically you can prove to yourself that RF is important for that. A linear accelerator, you don't need to have RF, but eventually you can't stand off the voltage. So anyway, so that's the first thing to tell you, that you need RF to accelerate a beam. So RF cavities come in all sorts of different types, shapes, and flavors. This is a booster cavity in the Fermilab tunnel. It's a very old cavity. It was designed in 1969. It's got tuners on the ends. It's a transmission leg type cavity. And it's kind of an example of a very old style cavity. All the rage now is these multi-cell superconducting cavities. Here, as you can see, basically they look like a beam pipe with a couple of convolutions in them. The electromagnetic understanding of these things is much simpler than that here. So basically going back into superconducting RF land actually takes the RF engineers a step backwards. So basically superconducting RF is great for plumbers and stuff like that, but it's kind of boring for RF guys. So anyway, so what we'll talk about is basically, we'll start mostly with the transmission line type cavity because it's very prevalent. You see it, and it's the approximation as you go to things. And then and you also know about transmission lines. And then these kind of concepts will generalize into this as well. In fact, you can kind of visualize how this type of cavity can go to a single cell if you pull the gaps back and you curve the edges. It basically is the same thing. Okay, so almost all cavities are basically the same thing. Okay. So the first thing to do is let's take a look at a cavity field pattern. So in a cavity field pattern, so for transmission line type cavity, you have a beam pipe comes through, there's a gap in the beam pipe, and then the beam pipe goes through the other side of the cavity, and then surrounding the beam pipe is a shell that stores the electromagnetic fields. All right? Now, these electromagnetic fields will oscillate inside the shell, and basically what you'll do for the accelerating mode, you can see that at the edge, this is a short circuit. So the electric fields has to grow, and then when you go over to the other side, you see that the electric fields actually flip sign, and then they go back down to the other side here, and this is, you can see you have an electric field that goes across here. The magnetic fields basically have to be zero in the center of the beam pipe because there's no current flowing on the center conductor, and the magnetic fields are a maximum at the edges. And we can use these two features to design couplers. But basically that's what the field pattern looks like. Okay, so people go ahead and then they need to solve what the cavity modes are in order to understand how well they're going to accelerate this. In the old days they did it with pencil and paper. These days everybody uses computer programs to do that. But it's very good to actually be able to do it on pencil and paper just so that you can understand how the computers work. So the first thing we're going to do is we're going to ignore the gap capacitance. Right? So we're going to basically sit there and solve only one half of the problem. And we're going to say, here is the short circuit at X equals L. Here's where the gap is. And we're just going to say, for the time being, forget about the gap. Right? So at this point here, we can say that we can solve it by symmetry. One side must be the same as the other. They look exactly the same. So for the cavity, it looks like a shorted section of transmission line. It's a short circuit here, and here's your transmission line, it's a short circuit. So you have a forward and a reverse wave, forward and reverse current wave. And Z0 again is the characteristic impedance of the structure. So at the boundary condition, you have to have the voltage that has to be equal to 0 at the short circuit end of the wall. So that means that V means that the incident reflected wave are given by minus signs, the reflection coefficient is minus, then V is equal to V0 sine beta x, because we chose x to be at the end of the wall. Okay? If you chose it different, you'd have to have a different place here. And then the current is Z0 times I is equal to minus J V0 cosine beta x. Okay, so that's boundary condition number 1. Boundary condition number 2 is that the gap, the current, has to be equal to 0. So at one end the voltage has to be equal to 0, at this end the current has to be equal to 0. So for the current to be equal to 0, that means cosine beta L is equal to 0, and this can only happen when this guy is equal to odd multiples of pi over 2. So this can happen for different, so if that means beta n times L, these different modes, beta n times L, have to be equal to odd multiples of pi over 2, or only certain frequencies will work in the cavity. So at any other frequency, the cavity rejects it. It just won't store energy. It's like a swing, all right? So you see a swing in a playground, you can push the swing, and it swings back and forth with a given resonant frequency. If you try to push it faster, it doesn't go faster. It just goes at the resonant frequency. So you just have to push the swing when the swing comes back at you, okay? And this is the same thing true here. You can only feel electromagnetic energy in the cavity when it's going to come back and resonate to you at these given frequencies. And the different frequencies are called modes. And usually the lowest value of n is called the fundamental mode of the cavity. All right, and not necessarily the case that the fundamental mode is going to be the accelerating mode. That doesn't the case. So here are the different cavity modes. This is the cavity mode for n equals 0. And you can see that the electric field comes up, maximizes, and goes back down. That's what I drew before. N equals 1, it comes up to 0, and then it gets to a minimum 3/4 of the way down the beam pipe, and then it comes back up again. Okay, so you have a null here, and the maximums here, and the null here. And you can see n equals 2, you get 2 nulls. N equals 3, you get 3 nulls, and so on. So you get more nulls in there. All right, now, you're going to look back at this and sit there and say, well, geez, how did you get off and do this? You could have had the electric field go in this direction just as well, right? You know, this is, you know, I drew it this way, but how come the electric field also goes down and points in the other direction either way? Well, it actually can. You can have the two modes happening at the same time. So we can take a look at even odd mode decomposition. So let's assume that we're going to drive the cavity on only one side of the transmission line. We're going to connect up the power amplifier, and we're going to connect it to one side of the transmission line here. So this voltage here that we apply to this cavity, we can decompose it to make it into even and odd mode symmetry. So I can write this voltage here as 1/2 V plus 1/2 V, and since it's 0 over here, I can write this as 1/2 V minus 1/2 V, okay, which is 0. Then what I could do is sit there and take a look at the even and the odd modes. So this would be the even mode. The voltages are the same on both sides. The odd mode is the voltages are different on both sides. Okay, so with the even mode, you have no field in the gap. Okay, but the cavity will resonate here, but there will be no field in the gap. So this is a disaster as far as an accelerating structure, because if there's no field in the gap, there's no acceleration. Okay. However, you'll put power into that mode, and you'll excite energy into that mode, so all your valuable klystron energy goes off into exciting stuff that you're not going to use. For the odd mode, you actually do get field in the gap. This is the one we want. This is the one that we have. So these two modes here are basically what we call the degenerate. Okay, and so even odd, they have the same frequencies. Modes that happen at the same frequency are called degenerate. And so the point is, just like in quantum mechanics, we want to split the degeneracy. Okay, so we need to split it in order to get the resonant frequency, in order to get only the mode that we would like to do that. So we can do that if we can include the gap capacitance. The gap capacitance, as you can see, destroys the symmetry. It goes across the thing, so you destroy the symmetry at this point. And in the even mode, since the voltage is the same across both sides of the gap, no capacitive current can flow through the gap. So if you got this even mode there, you'll not pull any, it's like the capacitor doesn't exist. In the odd mode, there's a voltage difference across the gap, therefore current will flow through that capacitor. So let's take a look at the gap capacitance. Boundary condition number 1. Okay, V is equal to, again, V0 sine beta x. It's got to be a short circuit at the end. And then the current is given by this. Now, boundary condition number 2, you're given this thing that the current has to be equal to the gap capacitance times the voltage across the gap. Okay? So that means that you have another boundary condition where this used to be 0, okay, or where this guy used to be had to be equal to 0. You now have that the current and the voltage are related. So here's the voltage, which is right here, V0 sine beta x. Here's the current, and they have to be related by the gap capacitance. And so that you have this is equal to, the gap capacitance is equal to 1 over the tangent of beta L. So, let's assume though, so this is a transcendental equation, which you have to solve numerically or graphically. So let's try to do this on a piece of paper. Let's assume that the gap capacitance is very small, and we're only going to perturb the gap capacitance. We're only going to perturb the mode frequency by a little bit. So we'll sit there and say the mode is going to be pi over 2 plus a little bit, which we don't know what the little bit is. But we can put pi over 2 back into the formulas, and you can see that cosine beta L over sine beta L is equal to minus delta. Okay? Therefore, this delta is equal to minus omega 0 CG Z0. So you can solve for omega 0, okay? And therefore you get that delta omega 0 over omega 0 is 2 over pi delta. And so basically the gap capacitance shifts down the frequency and leaves the either mode frequency the same. Okay, so if you've done quantum mechanics or something like this, this is kind of standard things where you basically put in a small perturbation, it shifts the degenerate modes. That's like, for example, an atom. So when you have the orbits, there you have the L and the S and the J, okay, that actually splits, and that's when you get the fine structure and the hyperfine structure. So it's kind of the same thing that you're doing here. Okay, so I'm going to have to switch to my other plotter. So for each cell, so for multi-celled cavities, now this goes, so you can think of a transmission line type cavity as a multi-cell cavity. It's got 2 cells, 2 transmission lines, and they're connected by the middle by a gap capacity. So that's considered a 2-cell cavity. You could have had a 1-cell cavity. You could have just kept that short circuit over there and not put another transmission line there if you'd like to. People do that with cavities. They make that typically, what you'll see with most superconducting cavities at very low frequency are transmission line type cavities that look exactly like that. Unfortunately, they don't go through, or not unfortunately, but differently, they don't go through the beam pipe. They put the cavity perpendicular to that, and they basically go through the end of the nose of the beam pipe to do that. So you can do it. You can do it different ways. So what I'd like to do is show this. Hopefully this will work. I won't destroy things. Okay, cool. Okay, so each in multi-cell cavities, each cell has its own resonant frequency. So for n cells, there's going to be n degenerate modes that you have. The cavity coupling between the cells splits the degenerate modes. So if you have an ILC cavity which has 9 cells, you're going to have 9 different modes into this cavity. Okay, and people that worked at the Fermilab where they see the long structures of cavities, there's many modes onto those things. So only one mode is going to be right, which is basically the pi mode that most people want to operate in here. The pi mode means that these guys are in opposite phase to each other, and by the time it comes over, the phase switches and you get the right accelerating voltage. So only one mode actually works for these cavities. This is what's called the pi mode through the cavities. You don't have to design it for the pi mode, but people typically design multi-cell cavities for the pi mode. So let me just go back, because this will be dangerous. Alright, so again, so how do you do that? What do people do? They actually have to design, this coupling here is a very key part to designing superconducting cavities. This coupling factor tells you how the modes are going to be split. And it's important to make the modes split because otherwise sometimes the beam can excite some of the modes in there. And so if anybody has ever taken I've talked to a lot of people, I know you guys go at Fermilab, but they have on the sides of the cavities, they have lots of little dimple holes.
And those were used for guys to tune up the cavities, okay, to be able to get the modes right, to be able to split them. So you do a bead pull, and sometimes you need to get it right, you need to do the perturbation right. At ESS, what we did is we actually built a 5-cell cavity at ESS for the modes. And then what we have is we have a thing we're going to talk about in higher order modes. And what happened is the manufacturer didn't hold the tolerance tight enough between the different cells. And what happened is that the higher order modes showed up at the wrong place in the spectrum because we didn't hold the tolerances. And basically that expensive piece of superconducting cavity is now a garbage can. Okay, so it's really important that you manage these things. So it's a very difficult thing to do, okay, especially when it's going to cool down by 450 degrees. Right. Okay, so now we've talked about modes. Okay, so we've understand the idea about how to store energy in the mode. You can only put these in at frequencies. Now, the modes that we've talked about, we've assumed a perfect conducting cavity. So only exactly one frequency will work. No frequency whatsoever will work. That would be a pretty impossible cavity to work with, because if you only have to get the frequency exactly right, you can see on your oscillators they're not quite exactly where you would like them to be. So you have to. So that would be a wonderfully infinitely stored cavity, but it would actually be impractical to use. So the cavity walls are lossless. It only happens at one frequency. But if they have some loss, then you can solve the boundary conditions over a range of frequencies. So people introduced this thing called the quality factor, Q. It's a convenient way to describe the loss in the cavity. Okay? So the Q is the Q factor, and it's for any resonator. It doesn't have to be an electromagnetic cavity. Any resonator is defined as the energy stored in the cavity divided by the energy lost per cycle. That's the definition of the Q. So it's a dimensionless number. So this is both energy, and that's both energy. So the energy lost in the cycle is given by the power lost in a cycle given by the time in a cycle. Okay, so this is basically, this is the electric energy, here's the magnetic energy, here's the power lost, and this is the time of the period of a cycle. Okay, so you can write it this way. So using so now what we're going to do is we're going to assume that the walls are hardly lossless, hardly have any loss at all. So we can assume again that the cavity modes haven't changed much. They're pretty much the same. Okay, so we'll take a look at the fundamental mode. You can take a look at the electrical energy that's stored in the cavity, and you just basically integrate that, the electric field squared over the volume of the cavity. And using the transmission line equations that we had there, you can go work through this, and you can get enough formula for the electric energy that's stored in there. You can also do the same thing for the magnetic energy, and you can see that the electric energy and the magnetic energy are same. That's usually the case. It doesn't have to be, but it's usually the case where the electric energy and the magnetic energy are the same. Okay, so now, what about the power that's lost in the cavity? Let's assume that there's a small resistive loss of R ohms per unit meter along the walls of the cavity. Assume that it doesn't perturb the distribution of the field. It's basically the same. If it was a very lossy cavity, yeah, you'd actually start to see that the fields decay away. So the power loss then is you just basically have to integrate the current squared times the resistance per unit length over the length of the cavity. You know what the current is from the equations, and so you can get basically the power loss in the cavity is given by this formula here. Okay, so the cavity Q for the fundamental mode of the transmission line cavity is given by two things. Here you have Z0 on top, and that makes sense because the higher the Z0, the less current that flows through the walls. And down here, this is the resistance in the walls. The less resistance in the walls, okay, the better it is. Okay. All right, so you can go ahead and do that for cavity Q, but that's actually pretty hard to do to each one of these things. If you're actually going to do this on HFSS, it takes a long time to do it and a lot of complications to do it. And it's hard then for RF engineers to decide what they're going to do with the klystrons. So one of the simplest things to do is people come up with an RLC model of a cavity. You could use a pendulum model if you wanted to, but we'll use an RLC cavity. And we'll have two things. We'll have a generator that's exciting the cavity, and we'll have a voltage that's going to be put across the gap. We'll have some magnetic energy storage here, some electric energy stored here, and we'll have some loss introduced to the cavity. Okay, so those are the three major components. We store electric, magnetic, and we lose some energy in the cavity. Okay, so
if you go through those little equations you have, you can come up with basically what's the equivalent resistance, it's shown here, what's the equivalent capacitance, what's the equivalent inductance, okay? All right, so you can come up and come up with these three equations based on your mode. So one ways that you might do this is you might go off and do this with HFSS. You can say what's the electric energy stored, what's the magnetic energy stored, what's the loss in the cavity, and I can come up with these three parameters. And these three parameters basically tell you everything you need to know about the cavity. So the transfer impedance of the cavity, this is what we want to know. We're paying for a klystron, and we want voltage across the gap. So how much voltage across the gap do we get as far as generator current? Okay? Most power sources you can kind of think as a current source with some impedance onto it. We'll talk about that in a second. So that's what's called the transfer impedance of the cavity. And it's just the parallel combination of R, L, and C as you go through that. So what you get then is you get basically, you can also do a little bit more combinations. Instead of doing R, L, and C, you can kind of group things together in terms of omega 0, R over Q, and Q. So you can use either R, L, or C, or omega 0, R over Q, and Q. Okay? Either three of those things are equivalent ways of describing the cavity. So when someone gives you a cavity, you ask them for three numbers. What's your omega 0, what's your R over Q, and what's your Q? And it's kind of important to realize that, for example, omega 0 and R over Q are a function only of the geometry. So you don't have to know anything about the walls, it's just given by the shape of the cavities. All right? One is given by the product, one is given by the ratio. All right? The other thing, though, is the Q is a function of the cavity geometry and the type of material that you use. So you can write the cavity impedance is given by this formula. So if you're in cavity world, you're going to use this formula a lot. You're going to use the R over Q of the cavity, and then basically given by this formula here, which is a plot here, which is just basically a parabola. This is a very important parameter called R over Q. Yeah?
So how come we have more than 3 parameters when we design a cavity in terms of geometry?
Okay, so if you're doing a multi-cell cavity, you're talking about multi-cell cavity, right? You have many parameters. Okay, so for superconducting cavity, there's recipes and rules in order to basically, besides, so as far as the RF guy is concerned, the guy that's designing the klystron system, he only needs to know 3 parameters. Now, there's other people that are worried about things. They want to know what's my maximum field I'm going to go to? When am I going to quench my superconducting cavity? So, for example, you can have very sharp nose cones, and those will give you a really high R over Q. Great thing to have, okay? Because you really want a high R over Q if you really don't have any beam loading and you don't want to pay for much power. You'd like to have as big as R over Q. But if you design a superconducting cavity with a very high R over Q, you're going to get intense fields at the nose cones and they'll quench. Okay, so basically there's a bunch of recipes, and I'm not a superconducting cavity designer, but about the A's and the B's and the gaps and stuff like that, they work with those recipes. Another thing that I didn't tell you about multi-cell cavities is it's basically given by the fill time of the cavities. So when you fill the cavity up, you have to fill cell by cell by cell. It's a standing wave at the end, but when you're filling it, it's not a standing wave, it's a traveling wave. So you have to worry about how you fill the cavity as well. It gives it a certain thing that people would like to know on how well you fill it, because how slow you fill the cavity tells you how sensitive you're going to be to field flatness. Okay, so normally the cavity I drew there, all the cavities will have a flat field as I draw the lines perfect. But if I go through the manufacturing process, I might have small errors on the gap. And if I have a cavity that takes a long time to fill, that's going to be real sensitive to field flatness, okay, compared to a cavity that doesn't take a long time to fill. So these are all the parameters that a host of other people will ask for. But as far as an RF engineer is concerned, your job is just to get the RF power into the cavity. The physicists might, and the material science people might have other parameters, okay? All right.
Okay, so if you plot this curve, you can do two plots. One is basically, this is the real part, this is the magnitude is the red curve. And then you have the real part, and you have the imaginary part. And then you could or you can plot the real part of the magnitude, and you can plot the phase. And the phase is the phase of the voltage across the gap with respect to the generator that you're putting in. That's the phase, okay? So when you're on resonance, when you're at the resonance, this is at the peak.
okay, you get the maximum amount of impedance of the cavity, and the phase is equal to 0. And at that point, the inductors and the capacitors are balancing each other out. So whatever's going through the inductor is being balanced by the capacitor, and they cancel, the impedance cancels each other out, and all you're left is the impedance of the resistor going through there. So if you have an infinite resistance cavity, a superconducting cavity, this goes like that, okay? If you have a low resistance cavity, it goes like this, all right? But at the center, the phase is 0. That's because the inductors and capacitors are balancing each other out. The other thing to take a look is that a couple other interesting places. The places where basically the real and the imaginary part are equal, the phase, of course, would be 45 degrees. That's the definition of the real and imaginary part equal. And you see then the response is at the square root of 2 down. When the response is down at the square root of 2 down, if the power is going to be equal to that squared, okay, then basically the power, that's at the 1/2 power points. So the places where the real part and the imaginary part are equal or opposite each other are the places where I'm going to be at 1/2 power, or 1/2 power there. And these width here is given by, the width is given by the Q of the cavity. So the places where the real and imaginary part is equal to spacing here, that's given by the Q of the cavity. So just by looking at this transfer function, you can get the resonant frequency and you can get the Q of the cavity. But you can't get the R over Q. That's the only thing you can't get. Now, we're going to talk about this. You're not going to get quite the Q of the cavity that you think you're getting. You're going to get the Q of the cavity distorted by your probe that you're putting in there. Okay, so let's take a look at a simple pillbox cavity. So here you have a pillbox cavity. It's a TM mode, which is a higher order mode in the cavity. So it's a TM mode in which the magnetic field goes like this, okay? And then the electric field is like this and like that, all right? Okay, so that's the TM mode in the cavity. It has current on the walls of the cavity because you have the magnetic field like this. So the surface current runs along the walls in this direction here. And so each mode has a different R, L, and C. So you can see all the modes, they have different widths as you go through there. So you can't just take your R, L, and C of here and apply it to over here. And you're going to see that when we do the cavity measurements, that the R, L's, and C's for each one of the modes is different, okay, because the mode pattern inside. Okay, so now we understand the modes, we understand we can put it at different frequencies. Now we have to get energy into the cavities. So how do we get the energy into the cavities? We have to hook up something into the cavity. And I'll just do something pretty straightforward. I'll just hook up a little probe onto the center conductor of the cavity. And I'll ignore the inductance of this little wire here for the time being, right? Now, what I can take a look at this is you can see the voltage in the cavity goes down like this, and the current goes up like that, all right? So if I was to put the probe here, there's no current there, right? So the impedance that I would see into that cavity would be very high. So if I have a 50 ohm amplifier on here, I'm going to have a lot of power getting reflected back off that because the impedance is going to be too high. If I put the probe down here, it's basically a short circuit. So basically, it would have to have a very low impedance amplifier. By sliding the probe somewhere along here, I can tune what the impedance is going to look like at this point, and I can now basically present an impedance looking into the cavity. Okay, so you'll see that people will monkey with the locations of the probe. So that's a brute force way of doing things. And the way to take a look at this is basically, you should think of the coupler as a transformer that sits on the cavity. Here's my generator, here's my L, R, and C of the cavity, and my coupler can be thought of as a transformer, a one-to-n step-up transformer. Because your klystron or something, you maybe want at low impedance, but your cavity you definitely want to put up at high impedance. So you can think of your coupler as kind of an impedance transformer, and the impedance that you see at the PA is given by 1 over n squared, where this is some artificial turns of your transformer. There's really no transformer in there, but you're saying there's a mythical transformer that I can represent as my coupler. So the model is, here's the magnetic energy stored in the cavity, here's the electric energy stored in the cavity, here's the loss in the cavity, here's how my coupler is, here's my generator. Okay, now, we might not want to do that exactly by putting a probe right into the beam pipe, so there are different types of couplings. We can actually do it's either a BDOT probe or what's called an inductive probe, in which we basically can put a little square of coupling area into the probe, into the cavity. you can see that the square now encloses magnetic field. So that changing magnetic field in here will induce a voltage. Or a changing voltage around here will induce a changing magnetic field. Either way you want to do that. So basically now, we don't have to attach this directly to the beam pipe. We can excite the magnetic field in here. Okay? And this might be something that you want to do for very low impedance drivers. Okay? Another way you can actually put the probe in here is that you can, and basically, I want to go back up. The transformer ratio is given by the total flux here, given by the amount of coupler flux that you have. That's the transformer ratio, just like you would with any transformer. So this could be like the step-up transformer. Here's the big ends, here's the little end. All right, another way to do this is not exactly touch the probe to the cavity. You got to realize that basically this transmission line has some capacitance per unit length going from here to there. So I can think of this as maybe having an imaginary little capacitor, two capacitors in series, one going from here to here, and one going from here to here, and I'm touching the capacitor in the middle. Okay, so that's one way to take a look at this. And so now the equivalent capacitance is just given by 1 over C1 plus 1 over C2, and you can see the impedance of the PA is just given by the C2 capacitance divided by the equivalent capacitance there. So by changing that probe, you can actually change the impedance. You bring the probe real close, the impedance is going to be low. You bring the probe away, the impedance is going to be high. Okay, so those are a couple ways of people building couplers. And in general, what they do is they do this with HFSS or something like this to really tune these things out. They'll put all sorts of doorknobs on that. One of the things that you'll see, maybe, I'm not sure if we have some of these in here, I'm sure if Ralph brought some of the old stochastic cooling boards, probably not, is that you'll see these things have these very complicated shapes. And you guys, how did you guys do that? You're geniuses. Well, what we did is we put a simple shape down, and then we took an X-Acto knife, and we looked at things like time domain reflectometers, or we looked at instruments, and we just kind of hacked and carved until we got what we wanted to. It was kind of like craftsmen of the old world way of doing things. All right, so, and you'll see that sometimes in these couplers. You look inside for example, a coaxial to waveguide coupler, and you'll see screws sticking out. You go, what the heck are those for? That's because somebody stuck them in there, and they twiddled them enough to get what they wanted, and that's how it goes. Okay, so far we've been ignoring the internal resistance of the power amplifier. This is a good approximation for tetrode amplifiers such as the Fermi-LED, such as the booster and the injector. This is really a bad approximation for superconducting cavities. In fact, it's a terrible approximation because the generator impedance is much lower than the cavity impedance. Okay, so this is basically, in the case of the tetrode has a very high impedance compared to the cavities, so you can kind of get away with that. So every power amplifier has some internal resistance. Okay, you have some current, and basically there's some voltage variation as you change the current in there. They're not perfectly stiff current supplies. They have their softness to it. Okay, so what you can now do is you can put another model here, is you have your coupler here, and now you add your generator impedance here. So you basically now have a complete circuit seen by the cavity of a resistance here given by the cavity walls, but now you have an N squared R resistance that's given by the generator. And the generator current goes down by 1 over N. So I've pushed the circuit through the transformer to get this equivalent circuit here. So now you can see that my generator is in parallel with this guy. Being in parallel means he's going to introduce more loss. Okay, so the generator resistance in parallel with the cavity resistance, this means the total resistance is now lowered. And so now what we have, the power amplifier internal resistance makes the total Q of the circuit small. That means that the Q of the circuit, the loaded Q, so we've loaded this down with our generator, is given by 1 over Q0 plus 1 over Q external. For our transmission line cavity, we had QL equal to this, we had Q0 equal to this, and therefore our Q external is given by this term here. Okay? So what happens now, yes?
So loaded means you take into account the voltage of the generator.
Right. So when you have a loaded Q, it means you put some load across your cavity gap. Okay. So you have so it doesn't have to be the generator, but it typically means the generator. Okay. So when you have your unloaded Q, your Q0, that's the cavity all by itself, and that's something you really can never exactly measure because you never have the cavity all by itself. Otherwise, it's worthless. It's just sitting there like this. In some cases, people can do that when they have put cavities into the beam pipe of accelerators to do self-bunching and things like that. They make a impedance and purpose to do that thing. Okay, if you tune the cavities right, you can get them to kind of the beam to self-bunch by that. But normally, you put some kind of power amplifier in it. As soon as you put a power amplifier on that, you're going to take down the cavity bandwidth. You're going to put some loss across it when you do that.
Okay, so, oops. Okay, now, so the cavity, again, is usually attached to the power amplifier by a transmission line. Again, in the case of a lot of old-style cavities, that transmission line is infinitesimally short. The power amplifier sits right on top of the cavity. But in most cases, your cavity's downstairs, your klystron's upstairs, and you have some type of transmission line in between them. Right? So we can actually think of our model from the power amplifier point of view world, which is where the world we're going to want to live in, is we basically have our power amplifier, we have a transmission line, the cavity coupler. So now we've added another piece into the puzzle. Okay, from the power amplifier point of view, okay, you can see here's our transmission line, and then everybody gets shifted down by 1 over n squared, except for the capacity goes up by n squared, and the voltage in the gap goes down by n. You can see now that you have basically an impedance at resonance. This guy cancels that guy, right? And we're probably much going to run the cavity at resonance. We're going to want to run the cavity at resonance. So we have this resistance here, and we have this resistance here, and what we would really like to do is get all the power we can into this guy here. So typically what you do is you match Z0 to the generator, right? Okay, that would be foolish to not buy an amplifier in which you don't. In some cases, there are cases we don't, but typically you match your generator to the amplifier. And then what you'd actually like to do is you'd like to match your cavity to the transmission line, okay? So that you get the maximum amount of power. But you're never going to actually be able to do this in all cases. So you have 3 cases. One in which we're going to take a look at this coupling impedance, and that's given by this equivalent resistance divided by Z0. When this guy is less, okay, this resistance looks less than a Z0, that's called undercoupled. When this resistance is equal to 1, it's critically coupled. When this resistance is over 1, it's overcoupled. Okay, as far as, so those are the different things that people say. I'm undercoupled, I'm critically coupled, I'm overcoupled. Okay, so which coupling is the best? Critically coupled would provide a maximum transfer to the cavity. So, however, some power amplifiers, such as tetrodes, have a very high internal resistance that you're often undercoupled. Okay, all right. However, some cavities have extremely low losses, so that you're overcoupled. So, superconducting cavities, you are just super overcoupled. There's no way you're ever going to be critically coupled in a superconducting cavity. Okay. So what you have to use with a superconducting cavity, which we're not going to talk about in this class, is you're going to have to sit there and get the power into the beam, because the beam actually is where you're putting the power to. In most cases, we've ignored the beam here. So this is all done without any beam loading. With a superconducting cavity, you have beam loading, and there you have to take the impedance of the beam. Okay, so now, how do we measure the cavity coupling? Here's the frequency response of the cavity at the given mode, is given by this, which we can actually rewrite in a nice, even simpler formula. It's given by R cosine phi e to the j phi, where phi is given by the frequency and the Q. Okay, so this is just a parameter phi here. This makes life really easy to do. This is complicated, this is easy. Right? So the reflection coefficient, as seen by the power amplifier, is given by the cavity impedance, given by the transformation of the transmission line up, and you can then substitute this in. You can see your reflection coefficient. This is the cavity impedance. This is the characteristic impedance of the transmission line. This traces out a circle on the UV plane. Okay, and here's the circle that it traces out on the gamma plane. So it kind of looks like a Smith chart flipped over. So you see that there's a radius. The radius of the circle is given by R coupling over R coupling plus 1. The center is given by minus 1 over R coupling from here. And the left edge always sits here. And the right edge always sits R coupling minus 1 over R coupling plus 1. So what you can do, this trace here is as you sweep the frequency. And you're going to see this actually in the cavity. It's amazing. It actually it plots out a circle.
And that shows you how well that parallel LRC model works. For most cavity modes, it works really well. You say, oh, that looks too simple, but that parallel LRC model is pretty good. And it traces out the circle. Now if I know this circle, boom, I can measure this value here, and I can know where my cavity coupling is. So basically, if this guy goes all the way and touches this guy right here, I know that I'm critically coupled. Now I can see that I'm undercoupled. If the circle's bigger than this, I can see that I'm overcoupled. Okay, so the cavity coupling can be determined by measuring the reflection coefficient on the Smith chart, and then you just read off the resistance here, and zingo, you got your cavity coupling right away. So the first thing you can do is measure cavity coupling that way. Okay, so again, here's the different cases of undercoupled, critically coupled, and overcoupled. All right, now, measuring the loaded Q of the cavity. Okay, so that's actually straightforward. The simplest way to measure the cavity response is to drive the cavity with the coupler and then have a very light probe sitting here at all. This very light probe is very close to the sides of the wall, so its transformer ratio is extremely high, right? So that means he's going to present a very high impedance here, and so that we're lightly going to disturb the cavity here. So this guy's impedance really doesn't make this thing. So if the impedance looking this way is much less or much higher than the impedance looking this way, then basically I can measure the loaded Q of the cavity. If I really load it hard, then it has a problem with that. And then what I do is I put a signal in here, and I measure the RF output, and I measure S21. And I will sweep this cavity impedance that will look like this. And you guys will do this here. Now, it depends on, this resonance width will depend on how much coupling you have. So you will see here, you're only going to be measuring the loaded Q, because you're loading the cavity with this thing here. Okay, so when most people measure S21, they're always measuring the loaded Q of the cavity. Okay, but you've spent all this money trying to build very high performance things onto your cavity. You want to measure the unloaded Q of your cavity. How good is your copper, for example? It's very hard to do this technique with superconducting cavities. Usually you do this with a ring technique in a vertical test. Okay, so if the coupling is not too extreme, that means it's not too critically coupled or not too undercoupled, not too overcoupled, you can basically use this for the S11 measurements of the coupler. So what you can do is that at the unloaded Q of the cavity, the impedance of the imaginary part of the cavity is going to be equal to the real part of the cavity. So if I'm looking at the cavity, and I say, what's the impedance at the place where I'm equal to the real part is equal to the imaginary part, okay, that's given by the unloaded Q0. So what I can do is measure the frequencies in which the real part is equal to the imaginary part. When I do that, I measure Q0. So that's the only way you can measure Q0 with a network analyzer. Otherwise, you have to put it in a vertical test with a very lightly coupled, extremely lightly coupled thing, and ring it down. You hit it, and it rings down, and you measure the decay time with the ring time. That's the other way to do that. That's how you do it with superconducting cavities. But the minute you put the power amplifier on it, you can never measure Q0, okay, for our superconducting cavity. You can only do this with vertical tests. Okay, so you can see here, this is the place where the real part is equal to the imaginary part. Okay, you take a look at this frequency, take a look at that frequency, and then you can compute Q0. And we're going to do that for our cavities. And you measure Q sub L. And you're going to be asked what is derived knowing the cavity coupling and knowing Q0, what's the Q sub L? And then check that with S21. So from strictly an S11 measurement, I can measure the cavity coupling by knowing this thing here. I can measure the Q0 by knowing this thing here. And therefore I can measure the unloaded Q as well. And the loaded Q.
How do you get all those off the Smith chart?
Yes.
How do you get omega naught off the Smith chart? How do you get?
So omega naught here is you're going to get this with your network analyzer. Okay. So you're going to sweep this. You're going to sweep your frequency until this guy gets to here.
I mean, the thing the arrow is pointing at for omega naught, that's not telling you what the omega naught is.
No, that's at that frequency. So to get this curve, I've had to sweep my network analyzer. So my network analyzer makes measurements at different frequencies. I'm going to sweep that. As I sweep the network analyzer, I trace out this curve. Okay?
Okay.
So when this thing hits this axis here,
or it goes the furthest extension, that's gonna be omega 0.
Whatever frequency it was when it's moving, when it crosses the
Yeah, when it crosses, when it goes here. When it goes from here to here, that's where the real part is equal to the imaginary part. I record those frequencies, and I can get the Q0. Okay? And then I can also measure what this value is on the Smith chart, and I can get the coupling. Therefore, I can, knowing all those numbers, I can also tell you what the loaded Q is, without even doing an S21 measurement, just from looking down at it. So I don't need to put that probe in there if I don't want to, except for superconducting cavities, you do. Okay, so basically, here's the formulas. We just talked about that here. You'll just do this in the lab. One of the things that I see people do all the time, I used to see this all the time at Fermilab, is this technique here. What they'll do is they'll take the reflection coefficient of a cavity and the S11, and they'll sweep it through, and they'll see the notch, and they'll measure the width of this and say, here's the Q in my cavity, and they'll tell you, I got really great Qs. This Q0 is unbelievably high. Okay, you'll have people doing that. Okay, and the reason why you never want to do that, the depth of this guy depends on the coupling value, right? If you're critically coupled, this guy will skyrocket down to 0. So if I go down to, or skyrocket down here, if I go here and measure 3 dB off, yeah, it's going to look tiny, but it has nothing to do with it does have something to do with the Q0 and the QL, but you got to know the coupling value to do that. This is just a really bad thing to do. Okay, so don't sweep S11 and look for the divot and measure the width, and actually have yourself say, I know what the cavity Q is. You need one more parameter. You need to know what the coupling value is if you're going to pull that stuff.
But if you minimize the coupling until it no longer changes, doesn't that get you pretty close though? I mean, if you pull back the coupling until you stop seeing it change.
If you critically couple here, and if you measure here and here, like the 10 dB points, okay, you can do it, but you have to know your coupling value from your S11 measurement.
But if you're highly undercoupled, if you're like really, really weakly coupled.
If you're really weakly coupled, then you still got to know what your coupling value is, right? If you're really undercoupled, you're like this, right?
Right.
So you could do it if you can still do this if you worked out the math. You could do the sweep of S11. You still need one extra piece of information. You need to look at the Smith chart to measure what the coupling value is.
But if the coupling value is so small that it's no longer affecting your result, that's what I'm saying. If you make the coupling so small that
Then this is a flat line. If the coupling value is so small, you never get any energy into the cavity. So
but it doesn't have to be 0, it just has to be small enough that it's not affecting.
but then you still have to know again how far from 0 it is. You still got to know. You can work out the math. We'll probably go after it later, but really it's a dangerous way to do it. You can do it, but you got to use the Smith chart to get the coupling value to know that. And since you've already went to the Smith chart, just do it the right way. Okay, beeples. So we've talked about Q0, Q spell, omega 0, but we haven't got what R over Q is. So now we'd like to know what R over Q is. Okay, and there's no way to do that from the power amplifier because the power amplifier can't get across that gap. It knows what voltage is at its terminals, but it doesn't know what it is across the gap. So how do you measure that? Okay, the simple way to do this is the bead pull setup. You take a bead and you string it through the cavity, and you pull the bead through the cavity, and it perturbs this bead as it goes through the cavity. It will perturb the electromagnetic fields and shift the resonance. And by measuring the shift in resonance, you can determine what the strength of the electric field was there before the bead got there. Okay, so there you measure it with the bead not there and with the bead there, and you can look at that shift and you can say the electric field must be this value there. Then you get a plot of the electric field going across the gap, then you know what R over Q is.
So the bead's just a dielectric, like just plastic, right?
We can use metal, so we'll use metal. So the best thing to do is to use a dielectric. Never use a metal wire, because the metal wire makes a TEM load run down the beam pipe, which then will make an impedance which will load the living daylights out of your beam pipe. So you need to put in a very lightly low dielectric fish line. Even if you put a heavy dielectric fish line, you can
get a mode that would run down the beam pipe, right? If you got a high dielectric in there. But typically, if you put like a nylon line and stuff like that. But you could use a metal bead, we'll look at the things. If you use a metal bead, you have to put it where the magnetic field is equal to 0. If you put the metal bead in the place where the magnetic field is not equal to 0, you're going to get surface currents to run on that, and you're going to distort the magnetic field and not the electric field. Okay, and so it's better to use a dielectric bead. The problem with the dielectric bead, it doesn't have sometimes enough oomph to do anything, so a lot of people use metal beads. Okay, so how does this thing work? So the capacitor of an RLC model, you have your capacitor there. You can think about putting a small little dielectric cube in here. Okay, so this is the bead. You put the dielectric cube. Assume that the cube doesn't distort the fields appreciably. So that changes the stored energy in the capacitor will change. Okay, so you can write out that here's the total stored energy in the capacitor. It's got the original energy plus the new energy sitting inside the cube. Okay, and then you can calculate now. So this is how you calculate the stored energy. All right, so that means that the stored energy then, that the capacitance will actually increase. You put a dielectric inside a capacitor, the capacitance increases. And that shift in capacitance will be given by the electric field at the point of the cube divided by the total voltage across the gap. Okay? And since that capacitance changes, the resonant frequency will shift by this effective capacitance. Put a capacitance in there, you shift the resonant frequency, and basically you can see how much you'll shift the resonant frequency. So, but it's not quite known right now because we don't know what V gap is, right? So, we know EC, we know the delta C, but we don't know what V gap is. Okay, so for omega very much smaller than 0, and for capacitance very small, the shift in frequency is about proportional to 1/2 delta C over the equivalent capacitance, which again is given by this formula, which is the electric field at the capacitance, given by the voltage at the gap. Okay, so it's given by the shift in energy that we put in there, divided by the total energy that we store in there. Had we used a metallic bead, we'd have to take into account the magnetic field. Okay, but we won't really put that in there. But we also will distort the field, so people put form factors in, and people have worked this out since World War II. And so basically there's these form factors that you can get for beads. Okay, for small metal bead, the form factor looks like this. Okay, so you can look this up for different shaped beads, long ones, skinny ones, round ones, all sorts of things. Okay, so in general, the shift in frequency is proportional to a form factor times the electric field at the bead squared divided by the total energy. This is what it's going to be. This is basically the shift in frequency there. And these are the two form factors. But from the definition of cavity Q, Q is just given by the stored energy over omega 0 power loss. Power loss is just given 1/2 V gap squared over the equivalent resistance. You can actually then put in for what WT is. You can substitute in for what WT. The WT is 1/2 omega 0 V gap squared REQ over Q. Okay? That's just moving equations around to do that. All right. So therefore, you realize that right now is that using these two things here, you have this formula here for this total stored energy. You could write then the electric field as a function of position over the voltage of your gap is given by the shift in frequency divided by 1/R/Q at this point here. And I know I'm going pretty fast through the equations, but one extra step here is you know that if you integrate the electric field across the gap, you have to get the voltage across the gap. So you integrate that equation across the gap, and basically now you get R/Q is just given by the integral of that shift in frequency over the gap, okay, given by your form factor. So if you know your form factor with your bead, you put your bead at different places, you measure your shift in frequency, and you plot as a function of position, you integrate that function, and that's the R/Q. Okay, so now for bead pulls, what you could do is you're going to see this, and I see a lot of people do this all the time. You're going to shift the resonant frequency here. So you can see we're shifting the resonant frequency. Now, what is really the resonant frequency? Is it here? Is it there? Okay, there's a bit of uncertainty to it.
Okay, so if you measure the shift in resonant frequency, if the bead pull is very light, the bead's very light, then this isn't gonna shift much, okay? So it's much better to shift to look at the phase. So what you do is you take a look at, you get the phase centered up at 0 for the unperturbed thing, and then what you do is you you basically put the bead in there, and the phase gets shifted. Here, it's a slope, so it's actually much easier to measure. So you measure basically the phase difference between the drive and the receive, and that's a better way to measure it. So knowing that, the tangent of the phase shift is given by this formula here, and so basically your R over Q is given by this kind of your R equivalent of your gap is given by this total formula here, in which you just measure the phase shift across the gap. Okay? So you don't even need a network analyzer to do this. You basically need a bead on a string, you have a driver, and you have your gap detector, and you push them through a phase detector, and then you just measure the phase detector as a function of position. So you don't have to buy a fancy spectrum analyzer if you want to do bead pulls. Okay, so let's see where we're at. So that's at 10 o'clock. I think that would probably be a good place to stop. I do have some slides, they're in there, the notes, to talk about amplifiers, and I don't think that's really inside the scope of this class, so I think it would be good if we just kind of break here, and I think that's kind of enough. This will all come a lot more clear when you actually have to do the bead pulls and the cavity column. Okay, any questions? Okay. So we'll break for 15 minutes, Ralph?
15 minutes, yeah, sure.